We learned yesterday that when light of sufficient frequency, I'm talking about something like an X-ray or a gamma ray, something that has a really, really high frequency and therefore really, really high energy, when it strikes a metallic surface, an electron will be ejected. Of course it will. We would have predicted that with the photoelectric effect. But there will be sometimes a second photon ejected as well. Classical theory doesn't describe this, or at least doesn't describe the observations properly. Let me give you an analogy to help you to understand. The truck and the car again. The car is sitting on the side of the road. It's the electron. The truck is the photon, the high energy photon. The truck hits the car. The car gets bumped off the road. The electron has been ejected. The truck scatters. The truck bounces off as well. What do we know about the truck that bounced off versus the truck that struck the car? It's the same truck, right? Classical theory would predict that when a photon strikes the electron, if there is a photon that bounces off, it's going to be the same photon. The truck that bounced off the car was the same truck. The photon that bounces off the electron will be the same photon. But let's take a look at it a little bit closer. We do know that the truck will have less energy than the truck did when it struck it. Right? The truck, when it strikes the car, has a certain amount of energy. The car takes a little bit of energy away from it, and now the truck bounces off with less energy than it had before. If the photon bounces off with less energy than it had before, then it will have a smaller frequency than it had before, because energy is related to frequency. And if it has a smaller frequency, we've got a new type of EMR, a new frequency or a new type of EMR. So classical theory that predicted the photon would be the same as the photon that struck it is wrong. Okay, just like classical theory, in a sense, would predict the truck that bounces off would be the same truck. It is the same truck, but it has a lower energy than it had before, as does the photon that bounces off have a lower energy than it does before. In the context of a photon, though, it's going to have not just a lower energy, but a smaller frequency as well. In order to explain that, you need to know that energy is related to frequency. Einstein's photon theory. In other words, classical theory doesn't explain the fact that the photon changes. Photon theory or quantum theory, post-Einstein, does explain that the photon would be different than the initial photon. All right? So we had all kinds of evidence for the wave theory of light, the wave nature of light, diffraction, interference, polarization, refraction. We have the photoelectric effect to support the particle theory of light, and now we have the Compton effect, which also supports the particle theory of light. What's the big takeaway from this? Big takeaway? Well, one more piece of evidence to support the particle nature of light, and photons have momentum, because that's the way that Compton analyzed this. He said, this is just a collision, and whenever we have a collision, we do conservation of momentum. But to do conservation of momentum, photons must have momentum. We derived a couple equations yesterday for the momentum of a photon. P is equal to h over lambda, and E is equal to P times C. Momentum of a photon, momentum of something without mass. This equation up here in the top left-hand corner, that's the one that we learned back in September. That tells us that particles with mass, like electrons or protons or baseballs, still find the momentum the same way as we did back in September. But if it doesn't have mass, if it's a photon, then we've got to use one of these equations. We also learned that we could apply conservation of energy and conservation of momentum to get this equation. If energy of the photon goes down, and it does, right? Because the truck lost energy when it hit the car, the photon loses energy when it gets ejected as a result of the Compton effect. If it loses energy, it gains wavelength. The wavelength increases. So delta lambda here in this equation is the increase in wavelength, h over mc times 1 minus cosine theta, which is the scattering angle of the photon. That's it. That's where we left off yesterday. Today what I want to do is go through a couple of examples. I think you're going to find them relatively straightforward, though. Just a quick reminder, you have this on the notes that I handed out to you yesterday. Again, evidence to support the wave nature of light. Talked about that probably dozens of times this unit. Evidence to support the particle nature, that's newer. We have the photoelectric effect and the Compton effect, both of which we've learned this week. All right, example number 1. It says calculate the energy and the momentum of a photon whose wavelength is 600 nanometers. But I'll tell you what, the energy of the photon, that's not new. We've known for several days how to find the energy of that photon. It's just hc over lambda. This is an equation that we can use with the Compton effect, but certainly it's not unique to the Compton effect. Anytime we have a photon, its energy is hc over lambda. Can we use joules here? Yeah. Can we use the electron volts? We could use the electron volts here. I'm going to stick with joules. Anytime I see a question that uses momentum, I'm going to go joules. So I'm going to say h is 6.63 times 10 to the negative 34 joule seconds, multiplied by the speed of light, 3 times 10 to the 8, and divide that by 600 times 10 to the minus 9 meters. We're going to get a value for the energy there of 3.32 times 10 to the minus 19 joules. You could have converted that to electron volts. Sorry, you could have used the 4.14 value and gotten that answer in electron volts, or you could, if you wanted to, convert this answer to electron volts. The only reason you do that, though, would be if the answer, the 4 options given to you in a question, were expressed in electron volts. Now, the momentum of a photon, we know that E is equal to P times C. We know that P is equal to H over lambda. Those are both on our data sheet, as is this one. Which one do you want to use to find the momentum of a photon? Yep. Yep, absolutely. You could say E is equal to P times C, P is equal to E over C. You just found the energy here of 3.32 times 10 to the negative 19 divided by the speed of light, 3 times 10 to the 8. And when you do that, you should get 1.11 times 10 to the negative 27. That could be either kilograms meters per second or newtons seconds. Either set of units is good for momentum. That's good. Anybody think of another way? Because I didn't actually do it this way, right? Which way did you do it, Anna? Oh, okay. So you did. Okay. So you can absolutely find momentum using h over lambda. Okay, and that's what you did? Okay, of course, we get 1.11 times 10 to the negative 27 Newton seconds. And then Anna found it this way, which is the way that I found it as well. But then she actually took that and went back to E equals P times C to find the energy using that equation. So I used the first one and the third one. She used the second one and the third one. And Matteo used the first one and the second one. They all work, right? Okay, they all work. They can make it work. They're all valid equations. They should be the right answer. By the way, we've shown you two ways to do this. Of course, you don't need to do it both ways, but it is a nice little check for us sometimes if you do it more than one way. All right, one more example for you here. This one says an X-ray of wavelength 0.0125 nanometers is scattered at an angle of 50 degrees. Determine the wavelength of the scattered photon. This is an initial wavelength. 0.0125 times 10 to the minus 9 meters. We're scattering this photon at an angle of 50 degrees. We want to find the final wavelength there. What do you want to try for this one? Yeah, the cos equation, right? We're going to say delta lambda is equal to h over mc times 1 minus cosine theta. Always use 6.63 for this one. Whenever you're dealing with one of these three new momentum equations, just use joules always. The mass of the electron, speed of light, times 1 minus cosine 55 degrees. We'll do this one on our calculator because it's a little bit ugly. say 6.63 times 10 to the minus 34, divide it by brackets on the bottom. That by 1 times 10 to the minus 31 times 3 times 10 to the 8. Is it 50? Yeah, it is close 50. Okay. So that gives me the number there, this big number right here. And then I have to multiply that by 1 minus cosine 50, not cos 55. So let's times that by bracket, 1 minus cosine 50, end both of those brackets. Gives me a value of 8.6656. 35 times 10 to the negative 13 meters. Done? If this is a multiple choice question, you guaranteed one of the 4 options is this one, right? RTQ, ATQ. Read the question, answer the question. What am I asked to find? The final wavelength. What have I found? The change in wavelength. So what are we going to do? Yeah, the change in wavelength is lambda f minus lambda I. If we want to solve for lambda f, we take the lambda I over by adding. Becomes lambda f is equal to delta lambda plus lambda I. We get a value for lambda f there of 1.3 times 10 to the minus 11.